Okay, welcome everyone to my continuation of what is algebra. Today we really will see the beginning of Galois theory. Strictly speaking, the name of this video is here, but really what it's all about is I would like to tell you where Galois theory in the end comes from. So the whole idea of Galois theory, if I would need to summarize it, would be that there are certain group actions or so certain symmetries on roots of polynomials. Okay, that's all good and well. We will see some examples. And kind of you want to formulate this in slightly different terms. So you have this symmetry on the roots, and you would like to formulate it in symmetries of the corresponding field extensions. So Galois theory then would like to study certain field extensions. They kind of correspond to, as I said, roots of polynomials in a nice way. And Galois theory then would like to make a statement like, okay, certain types of field extensions are reflected on the other side, on the symmetry side, as certain groups, as certain subgroups, as certain normal subgroups. And then you like to use group theory to say something about the field extensions. That's mostly how it goes, but it's a one-to-one correspondence. So you can also use field extensions to say something about groups. But usually you would like to use group theory to say something about field extensions. And in doing so, you actually say something about roots of polynomials. And yeah, we're talking about roots of polynomials here, solving polynomial equations. That's at the heart of mathematics, of course. And then this is an extremely important theory. But to get us all started, let's have a look at why should we expect groups to turn up? Well, what are groups? Well, for me, groups really appear in the wild. And for many people, that's actually the case. So what do I mean? Well, of course, you have the abstract definition of a group. Good. But that's not how I would like to think about a group. Why not? Well, because usually if you just write down an abstract definition, so here I have a set satisfying following properties, for example, A, B, C, D, E. Then if you would do this reasonably randomly, so without knowing what you're up to, then you usually end up with a non-theory. So your theory is relatively empty in the sense that you don't have any interesting examples. And that's again, that's a point. That's not how groups were constructed originally. Groups arise in the wild. So groups are symmetries of objects. That's kind of the slogan. Symmetries of certain objects, whatever those objects are. Today, of course, my objects will be fields. It's kind of the point. So symmetries of fields will be Galois groups. Basically, that's what it is. Um, but you might know, or if you have seen other videos about groups, so the standard examples, of course, are the groups of symmetry of certain geometric objects. And you all know, for example, the symmetry groups of platonic solids, which are, of course, those funny dice you usually see in whatever kind of pen and paper system, pen and paper role-playing game system, whatever. So you'll see them pretty often because they have this nice symmetry. So the tetrahedron, the octahedron, the cube, the icosahedron, and the dodecahedron, and the symmetry groups of are among the most well-studied groups ever. So people studied these symmetry groups and other symmetry groups, and then they kind of came up with an abstract definition of a group. That's basically what it was. Not quite, because there was also this story running in parallel, in complete parallel, that you have some nice solutions of roots, some nice roots of some polynomials. I will zoom into this picture in a second. And I mean, look at this. It looks like a square, so you definitely have a nice symmetry here. And turns out that these roots have the Z mod 2 cross Z mod 2 symmetry, basically given by one reflection in this direction and one reflection in this direction. So groups also arise as symmetries of polynomial equations, basically. And then the question is, Galois theory would like to reformulate the second part, so more the second part than the first one, in terms of fields. So let's have a look how this actually could go. So here's my zoomed in picture. And I clearly have this action by two elements that I would like to call f and g. And they're defined as follows. So f swaps the sign in front of square root of 2. So square root of 2 is here a solution of this polynomial. I will tell you later what this polynomial actually is. We'll see. But square root of 2 is one of the building blocks, not one of the solutions, one of the building blocks of those solutions. And the other one is the imaginary unit I. So I have basically two options. I can swap the sign in front of square root of 2, and I can swap the sign in front of I. So my G acts in this direction. It swaps the sign of I, and my F acts in this direction. It swaps the sign of square root of 2. So you clearly have this Klein foregroup, Z2 cross Z2, acting on this picture. And you would observe the following. And this is now the step from the roots to the field extensions. These are actually automorphisms of the field, of the corresponding field extension. In this case, I have my square root of 2 plus I field extension corresponding to those roots. If you like to think about it differently, it's also square root of I, square root of 2 and I. It's the same field extension. These are automorphisms of these field extensions, and not just arbitrary automorphisms. These are automorphisms that fix, well, kind of the field I would like to solve those polynomial equations in, which I can't, of course, but I want to kind of have this as a ground field. So they fix the rational numbers. And he would make the following funny observation, that the minimal polynomial of this element, which is kind of the building block of this whole symmetry, has actually the same degree as the order of my acting group. That's very important. So we'll see that in action in a second again. Just to be sure, let's do another example, a non-example. And this probably, you just do those two examples and you try to come up with the right notion yourself. So, I mean, okay, here is the solution of the polynomial x to the fifth minus 1 equals 0. The fifth roots of unities. And except the funny one, these are the so-called primitive roots of unities, and I just call them, I just call the first one here, I just call it zeta 5. It's one of the primitive fifth root of unities. And I mean, this is a pentagon. I just drew the pentagon for you. So obviously there's a Z mod 5 action on this, but this is wrong, because this Z mod 5 action on the roots is not an automorphism of my field. It doesn't fix the identity. That's the whole problem. And it also doesn't fix the rational numbers. So this is kind of the wrong action. And indeed, it is really wrong in the sense that the minimal polynomial of my generating element here is not of degree 5 as the order of the group, but it's of degree 4. And so in some sense, this action is not as good as the other action. And you would play around with more examples like this, and you will come up with a following definition or observation or whatever. So an automorphism, the symmetry of a field is just, so my fixed field is L. So L is my fixed field, and that's a big one. That's why I write L. It will be the L over K in a second. So L is a big field. So K is Q and L is kind of the big field where the roots live in. Anyway, so an automorphism of that field, it was, for example, this one here in this example. It's just what is the symmetry of a field? It's just a field automorphism, right? A symmetry of a field. And basically, the standard example of a group are automorphisms of an object. They usually form a group. The only thing you need to observe here is that composition of two field homomorphisms of fields is again an homomorphism of a field. And well, I just want them to be automorphisms. I want them to be bijective, so they're also invertible. In the inverse is also a field isomorphism. So these guys actually form a group. And that's not quite the group you want. You want this because here we had, so these are kind of a little bit strange and they do not fix Q. So you want to build in this condition. And the way you do it is you take a subgroup. This is now how this condition of the fixed field comes in. And you have a fixed field corresponding to that subgroup, which are just all elements which are invariant, which are not moved by your group, right? So just all elements that are invariant, not moved by your group. And then you have the funny statement. So now my K here, my little k, is actually the fixed field for a certain group. And then you can compute everything basically you want from there. So for example, the degree of field extensions is just the orbit under this, the size of the orbit under this action. So for any x, you have the orbit by just applying all your elements. I will show you the orbit in a second in an example, but you just apply all the elements of your group. So for example, the orbit here are those 4 points. Of this one, for example, the orbit are all 4 points because, well, I can go to the side using F, and I go from bottom to top using G. So the orbit here is everything. So this, you automatically know, if you know this abstract theory, that this is a degree 4 field extension. Without computing anything, basically. You need to compute the orbit. And kind of the whole point is this equation then, that you can actually write down the minimal polynomial by just looking at the orbit of a given element. So in this example, so I would like to know the minimal polynomial of this guy, and I just look at the orbit, take all the elements in the orbit. So this is plus minus square root of 2 plus minus I, that's the orbit. And I take the product of all of them. I just need to make sure, so this is really bad, so give me another shot. So just move this a little bit to the side. I just take this product. Okay, product of all the sides. Right? So just x minus the elements of the orbit. That's your minimal polynomial. And the fun is, it is absolutely not obvious if you have this factored, but if you would factor this out, then this actually would be in my fixed field. And my fixed field in this case is, so this L to the G in this case would be Q. So this polynomial is actually a polynomial with rational coefficients. Try to factor that, and you will see that this is actually true, which is a non-trivial statement. I mean, just looking at it, x minus, so yeah, this is my element here, x minus plus minus square root of 2 plus minus I. You take a product. There has to be some non-trivial cancellation in order to get rational numbers, but it works. And you know that by using this this abstract machinery of group actions on roots, on fields. Okay, so let me give you another example. Let me make this example better, namely make it work. So what you really need to do is you need to take out this element 1, because that's in your fixed ground field. It should be fixed by an automorphism. That's the whole point. And the automorphism you take could be, for example, this one, but it just squares all elements. So let me just write it like this. Okay. So here, this is angle 1, this is angle 2 if you want, and this would be 3, and the next one would be 4. And what you do is you square all elements. That means you send, let me write them again. Here you go. That just means you send this one to this one because you just squared. It has angle of normalized angle 1. So you just double it, normalized angle 2, you get to there. Doubling normalized angle 2 will get you to this one. So you want to avoid hitting this point because this should be fixed. That's why I'm doing it in this funny way. So this is angle 3. So you get all the way up to 6. 1, you jump over this one, you end up here to 6. And this is angle 4. So actually you get up 1, 2, 3, 4. So you get back to here. It looks a little bit like a funny action, but as you can see, this is just generating the group, which is now hidden. So let me move it to here. The group, this is just generating the group Z mod 4 in a very nice, well, maybe not very nice, but in a slightly strange way. But it, yeah. So I definitely will make a video about those field extensions corresponding to roots of unities, and you will see that this is actually not a completely bonkers way of doing it. It's not strange, but it's not as straightforward as this one, because this one doesn't work because you really want to avoid moving this point, because, well, that's what you get out of the abstract theory. And this action does exactly the right thing. It does fix my so I only permute basically those non-trivial roots, so those non-rational roots, and whoop, I permute them very nicely. And this does fix Q. So I know immediately that my minimal polynomial is actually this degree 4 polynomial, right? I just look at the orbit, and as you can see here, it's a circle, right? The orbit of this element, you jump to here, you jump to here, you jump to here, and you're back. So the orbit is everything. You just take the product over all of them. And again, it's not trivial that if you factor this out, then you will actually get a polynomial with coefficients over your fixed field. So my fixed field, again, is Q, LG. right? So polynomial in this coefficients, and indeed, if you factor this out, the polynomial, and this is not obvious, you really need to do this by hand, would be this one, x squared plus x plus 1, which is absolutely not obvious. And this is the minimal polynomial of my fifth root of unity, and not the one that you get from kind of the naive action, Anyway, let me wrap up. So in Galois theory, you want to study this extension, these group symmetries on roots, and you do it by studying certain field extensions, and you do that by realizing those group actions as automorphisms of a field. The automorphism of your field should kind of permute the roots in such a way that your fixed ground field is fixed. That's the whole point. So Q should stay fixed. And then you get some nice results like you can compute degrees of field extensions and you can construct the minimal polynomials. And the really amazing thing about it is I already like those results that you could construct the minimal polynomials. I showed you how it works, right? You could construct them as linear factors. And it's absolutely not obvious why they should, if you multiply them out, should get coefficients in let's say, in the rational numbers, but it works. So that's already an amazing statement. But what makes this whole story of Galois theory so good is that this is just the tip of the iceberg. It goes on and on and on. There's a really nice relationship between those automorphisms of the field and kind of group theory, subgroup theory, and so on. Anyway, I hope you enjoyed the video, and I also hope to see you next time.